Hi. No, not that page. Nope. Hi, Lily.
Hi.
Danny and Alec are still muted and our video stopped. Yee. It's so early, I still have crickets and everything.
What?
I still have crickets and everything in my background. Because we live in kind of a forest.
Really pretty. Oh, I'm tired.
Same here. I just woke up 25 minutes ago.
Nice.
I woke up at 7 o'clock.
An hour ago.
You might hear a lot of loud sounds because my neighbors are getting new air conditioning and they have like 5 air conditioning trucks.
Oh no, it's okay.
I did that assignment. Not that one. Eat. Got that one. I have that one. Do I have this one?
I'll be right back. There you can see me now.
Hi, Danny.
Gang, how you doing?
Good.
Good. I'm letting another couple people log in. We had somebody who missed the message and showed up here, so I'm kind of checking at the front door, making sure a parent comes, okay? So give me just like a minute and I'll make sure everybody else comes in. Drew, ooh, my chair's loud. Hey, if it pulls up and says anybody is in the waiting room, just hit the button that says admit, okay? All right, come on up. All right, let me go make sure she's good to go. All right, they're all wound up.
Okay.
I'll put some over here by the door. So when you go out the door, I want you to do your hands because Drew opened the door for you. So it means he put his hands on the door.
No, you opened the door.
I did.
Yes, you opened the door. How do you forget who opens the door?
They run out of it. Okay. All right. So I'm sorry. All right. Here's your. Hey, Drew, you did that way from my computer. No.
Down.
All right, so let's do what we can do with who we've got, huh? So yeah, somebody missed the message and showed up here, and I didn't want anybody to get near anybody else. So, everybody hear me?
Yep.
You guys good? So let's see, who else is on? Okay, Alex, careful. Alec is on and Sky is on, even though we don't see faces. All right, cool. So first off, there was a little experiment I wanted to do this morning just to see, just a quick one. Not a real lab, but so this is just a little thermometer. Can you guys see? Well, let me see, does it focus at all?
Yes, I can see it.
Can you tell what temperature it is on there? Or is it too out of focus to be close up?
I think it's 70.
Yeah, it's about, yeah, that's right. It's like 72, I think is what it says. So what I'm gonna do is I'm gonna take it and put it in this little container right here. And I'm just gonna leave it for a few minutes, okay? Then we're gonna come back and see if it's still 72, okay? We're gonna do something with it in a bit. Don't play with that. You get it in your fingers. Yeah, leave it alone. Okay. So I didn't check yet to see if everybody got their homework uploaded. Is there anybody who had trouble getting it uploaded or?
I still need to upload my stuff.
Okay,
But-
no big deal.
What confused me, is for lab 3, they said that they said that 2 groups were gonna work together, but I'm not in a group.
Right. Sometimes it's just going to say that because that's just the printout and what it says. So you just ignore that part. For lab 3, it's it's a video and it rolled out at midnight. So it should be available to everybody now. And it's about separating mixtures. And the mixture that we separate in this lab is actually it's a solution with water and 2 different salts in it. And the process is called fractional crystallization. And it involves taking these 2 salts that have different solubility values. So basically there are some of them, one of them will dissolve in water at much lower temperatures than the other will. And so what we do is we take the 2 salts, put them in the water, and then we boil the water a couple different times, run it through this filtering apparatus, which is really kind of cool. And then, one of them will come out in the filter paper, and the other one, we just basically boil all the water off and it's still there. So it's really kind of an interesting lab, and it took a long time to do, but the whole thing's on the video, and it's a longer video because it's lots of steps. But I still think it was a lot of fun. And I've saved one of the beakers for you because I thought it would be fun for y'all to look at, but now nobody's here today. So anyway, let's go over your work, why don't we? And let me see, where is your stuff? Okay, so this was you guys, right? And then, for lab today, you can do it during our normal lab time, or like those of you who are always online, just do it whenever you want. And all the answers that you're gonna need, all the data you're gonna need is already included because it's my data from when I ran it to film it. So you'll use that to fill in your data table and everything. Does that make sense? Yeah, kinda?
Yeah. A little bit.
A little bit. So when you watch the lab video, there's data in it and it's already written down. So all you need to do is just copy as you go and make sure you understand what's going on. Now, I will
Okay.
tell you this, there's some math in this lab that's kind of more advanced math. You guys at, the middle school level or late elementary, I'm not worried about you getting the math down totally as much as I am about the older kids. But I think if you watch it, it'll still make sense. The numbers will make sense and why we do what we do will make sense. So you guys talked about classifying matter this week, right? So,
Right.
all right. So can somebody tell me what an element is and how does that compare to maybe like an atom that we learned about before?
Adam is
Wait a minute, they're getting stuff out. They're getting their books. Hang on, they're looking. Anybody want to tell me? So, what were you going to say, Drew? Were you going to say something?
I like different kinds of atoms.
There are different kinds of atoms, right? But what's
They're
an,
like different elements.
and there are different elements, right? So what's the difference between an element and an atom? Senya's got it. Go for it, Senya.
I know what an element is.
Okay, what's an element?
It is a substance that cannot be broken down into any other substances by chemical or physical means.
That a girl. All right, that's it. So your element is a substance that can't be broken down. So your atom is the what?
It's made up of.
Your atom is the
certain type of
smallest particle of that substance that still retains all those properties. So yeah, you can have an oxygen atom, sure, but oxygen in the typical environment doesn't go around by itself. It tends to go around linked up with other things, typically other oxygen. Usually, like all the oxygen air in the air that you're breathing is in a molecule form. It's usually two of them stuck together as opposed to,
Did you move
what's that? Hi, in Lily's frame. So,
Did you move my binder to put this stuff on?
what?
Did you move my binder to put this stuff on?
There's Abby. No, I didn't move your binder. Okay. Oh, that's trying to get Abby in right there. Sorry. All right, here we go.
Natalia's trying to get on.
I see. I just let her in, so she should show up in a minute. I was like, who is that? Is that Susie? You're totally backlit. All right. So yeah. So we're just talking about atoms versus elements for Abby, who's probably just popping in somewhere. There you go. All right. And then what are some things that what are some words you can use to describe compounds that you might see? Like how might you describe, if you saw a silver spoon, okay, how might you describe the silver? What are some words you might use?
Hard.
Lily, are you raising your hand? Are you just twirling your pencil around? Hard, Bruce says. That's good. What else? Like
Silver colored.
silver colored. Would you say it's shiny?
I guess so.
Okay, yeah.
Gold maybe.
And then sometimes you can also talk about whether it's reflective, whether it conducts electricity and heat, right?
It's reflective.
It's reflective. Yeah, very good. It is reflective. All right. So then I'm giving my thermometer just another couple minutes there. You guys also talked about two different types of mixtures. Can anybody tell me what the how are we describing mixtures? What are our two types of mixtures? They both start with H. Oh, Jocelyn's having trouble waking up. It's okay, Jocelyn. Welcome to morning. She's yawned like 4 times. What do we think? Anybody know two different types of mixtures?
A salad.
A salad. Okay, salad is a mixture. What kind of mixture? What'd you say, Senya?
Hydrogen and hydrogen oxide.
Okay.
cream.
Ice cream. Oh, wait. Jocelyn's got it. Heterogeneous. There you go. There you go. Very good. She gave it a shot. All right. So we have two main different types of mixtures. They're heterogeneous and homogeneous. So when we're doing science, it's helpful to know a lot of Greek and Latin roots. It really helps to know Greek and Latin roots. So when you look at hetero and homos, so hetero means different and homo means same. So if you see homogeneous, it's going to mean that you have basically everything is in the mixture is, it's not the same so much as it is, you can't separate the pieces just like, it's like a, how do I describe it? So like a Coca-Cola versus a, well, not Coca-Cola, because that's got a lot of stuff in it. Tea versus salad. So a salad would be heterogeneous. You can separate all the components, right?
And you can see all the components that it involves in.
Right, exactly. Like sand too. Now sand, you'd have to get a microscope to really see it well. But if you've ever looked at sand under a microscope, it has all kinds of little tiny grains, but they're all made from different minerals or rocks or shells or whatever. And then if you were to look at tea, well, tea's got, obviously it's got particles from the tea leaves that are dissolved into that solution, but you can't see them, right? You couldn't look at that and you know, separate the tea.
Or like ketchup involves like salt and tomatoes, but you can't define the salt from the tomatoes. It's all
Right.
together.
Right. So, but what you can do is you can separate a mixture by a physical means. So even if it's a, whoop, something crashed somewhere. So even if it is something like a solution, like in our lab where we have salt water, I mean, you couldn't separate that by hand, but you can separate it by boiling it, right? So if you boil the water off, the salt would remain. Like if you just took regular table salt, right? And you put it in a pan on the stove with water and you boil, the water would go away and you'd be left with the salt. So that's a physical means of separation. So if it's not a mixture, what is it? Do you guys know? You're gonna guess. If it's not a mixture, it's gonna be a compound. And compounds are combined chemically. You can't separate them using a physical means. So compounds have a chemical formula, right? So what's H2O?
Water.
Okay, and that is the chemical equation. It's a chemical formula for water. And when we look at that, let me see if I can get, there's my whiteboard. Let me see if I can get my whiteboard to go up for a second and I'll show you what I mean. So can you guys see my whiteboard?
Yep.
Okay, so if we were to do water,
H.
H2O, right? Boy, I put that O over, oh, my eraser doesn't work here? Oh, my eraser is supposed to work here on my stylus pen. Hello, I'm making such a mess. What do you know? All right, let's try that one again. There's my, well, now, okay. There's my O a little closer to where I put him way off to the east. So this is a compound and it has a chemical formula, and this would be, hey, Ella and Jules, this would be the chemical formula for this compound, right? And we know what's in it based on what we see here. So what element is this? Do you guys know?
Water.
Well, compound is water, the whole thing together.
Oh, hydrogen.
That's right. That's hydrogen.
2 hydrogen and 1 oxygen.
Right. 2 hydrogen and 1 oxygen. Very good. Very good. All right. So if we were to give it a chemical name, it wouldn't be water, right? But we know this is water. So we're going to get into chemical naming at some point in a couple weeks, and there's all these steps to follow. It's like a flow chart. If then, if then, if then. But for now, if we look at this, so Jocelyn just told us we have 2 hydrogens, right? I have to hold my monitor screen still. I really have trouble writing on this morning. Don't look at that one. 2 hydrogens, right? And how many oxygens do we have?
1.
1 oxygen. All right, now, what if I did, how do I change the color? Oh, no. What if I did this and put a 2 in front?
It's
So-
not water anymore.
It is still water
Oh.
because now I have 2 molecules of water instead of 1 molecule of water. How many hydrogens do I have now? Does anybody know?
4?
4. How do you know that? How did you figure it out?
I don't know. I just guessed.
Well, can anybody tell how we get 4?
You add the 2 and 2 together.
That's right. That's right. It's multiplying, right? Because we took one of these H2Os. This is a compound, right? And one of these H2Os. And if we added them together, we're going to
You'll
get,
get more H2O.
right, 1, 2, 3, 4. So it's going to be 4 H2Os. And then how many oxygens would we have?
Don't you have the same amount of whatever?
How many oxygens would we have if we had 2? Oh, go ahead. Yeah, you got it, girls. You got, yeah. Abby and Jules are saying, they're saying 2, and they're correct. So when you look at this as a molecule, as a compound, any kind of compound, all right, what you're going to see, I need to get better at this whiteboard thing if we're going to be doing this. So it's a multiplying thing. You're going to say 2 times 2 is 4, and we have 4 hydrogen. And then
2 oxygen.
times 2 times O, sorry, oxygen, is going to be 2 oxygen, right? So that's how, oh, good. That's how the compounds work. So when we, yeah, and then for mixtures, it doesn't look anything like that, because mixtures can be a combination of just elements on their own, or it can be a combination of molecules that are compounds already. So if you have a mixture, for example, and it is, because this is what's in our lab, okay? We have this guy here. What was he again?
H2O.
Yep, water. Okay, so we got water, and there are 2 other things in our lab that we used. One of them is this. Do you know what that is, anybody? Anybody know? Anybody ever seen it?
Oh,
Salt.
It's what now?
Salt.
Salt. That's good. It's a salt, right? Ooh, admit, Eleanor. Eleanor made it home. Yay. So it's sodium chloride, and that's a salt. And this is actually salt, the same salt you use at the table. So when you guys, toss a little salt on your French fries. Hey, Eleanor, good to see you again. So this is the same salt you use on your French fries and your scrambled eggs, okay? The other salt that's in our lab is this one.
HNO3.
Yeah. Oh, no, wait, it wasn't HNO3. It was KNO3. Sorry, I just wrote the wrong thing because I was looking at that H. Where's my eraser? Oh, there we go. KNO3. I was looking over here at that H. So this is potassium nitrate.
Potassium nitrate.
Yeah, who got that? Who did that? That was excellent.
Me.
Oh, okay. Is that Alec? Trying to see who it was speaking.
Yes.
There we go. Yeah, potassium nitrate. All right, so we got our potassium nitrate, and these 2 are both compounds, right? And they're inside of another compound, and together they're going to make a mixture. Now, could you have other things in a mixture that are just basic elemental form? Like, could you have a mixture that has that in it? That's just oxygen, how it tends to go around. Yep. Hey. Yes, you could. All right, so let's have a look at a couple more things, and then we'll go over any questions you guys have. So when you guys looked at the bottom of page 10 in your book, and it drew out some molecules for you, right?
Which page 10?
In your book, not your binder. So I'll draw them up here. But basically, it gave you a combination that looks like this.
OCO.
OCO.
Okay. So what's in this?
Carbon
Carbon and oxygen.
Yep.
Carbon and oxygen.
Carbon and oxygen. Very, very good. Okay. And this one we write as CO2. And does anybody know what it is?
Carbon.
Carbon dioxide.
Carbon dioxide. Right. And is that something common?
Yes.
Yeah, of course. It's actually what you exhale. It's one of the things you exhale when
That's what the plants breathe in, and they exhale oxygen, which we breathe in.
Right. Very good. That's absolutely right. It's actually, yeah, when we get talking about reactions a little more, photosynthesis, which is what plants do for their energy, versus respiration, which is what we do, are actually opposite. They're opposite reactions, total opposite, which is really kind of neat. All right, the next one in your book looks like this, and this is one we talked about already.
H2O.
Right. And it kind of looks like Mickey Mouse.
Water.
Yep.
Or the Mickey Mouse head.
Yep. It's H2O. You got that. Did everybody get that one?
Yep.
All right, cool. Are you looking in your book to see what you got? That doesn't look like your book to me. That doesn't look like your book at all. And then we talked about oxygen. He doesn't hang out by himself, right? He's always with the friend.
Lucky.
So he's just O2, right? You guys following me?
Mm.
Okay. So then the last one that it shows in your book, it has a big nitrogen in the middle.
And 3 little hydrogens.
It's got a hydrogen here, and it has a hydrogen here, and it has a hydrogen here.
So it looks like Mickey Mouse with an extra ear on its mouth.
Yeah, it does. Or kind of like a sad teddy bear, or I don't know, maybe a happy teddy bear. The one in your book has these guys kind of, they're a little more like down here, like sad teddy bear ears, like he's, I don't know. So,
Relatable to the bear.
and what's this one?
Ammonia.
That's right, and it's NH3, right? And that's ammonia. You guys use ammonia in your house for anything? Do you know? Where you might
I
find it?
don't know what it is.
It's usually in glass cleaner. If you look at
We
any
have-
glass cleaner, it
We
might-
actually have one with ammonia and without ammonia.
is there ammonia in that, Senya?
Yeah.
See, there you go. Yep. You'll find it a lot in glass cleaner. You'll find it in other things too. It also, it can be in urine. Yep. So you might find sometimes that, like if you have a puppy that has peed your rug 100 times and you're like, oh, it smells. That's probably one of the compounds that you're smelling. Or if you've ever been in a nursing home, I've had that pleasure. You're like, oh, look at the ammonia. All right, so what holds the hydrogen and oxygen atoms together in a water molecule?
Negative charges.
Yeah. What do we call that? So chemical bonds is what is holding things together. In particular, it's covalent. And we're going to get to different types of bonds later. But it's a chemical bond that holds your oxygen and your, there you go, your oxygen and hydrogen together in a water molecule. So this question on your homework said table sugar has a chemical formula of C12H12O11. So what's the ratio of carbon atoms to oxygen atoms?
12 to 11.
12 to 11, that's right, 12 to 11, perfect. Does everybody see why that is?
Yes.
Yep, so a ratio is when you're comparing two things. Now that's gonna come up in your lab too, because one of the things that we do in your lab is we're trying to figure out how much of our solution was potassium nitrate and how much of our solution was sodium chloride. So a percentage, it's a mass percentage, but the formula's in there. But it's going to, the way to find out how much you have deals with their mass, and there's a whole bunch of steps to the math, but I'm gonna show it to you before I just turn you loose on that lab. And basically, what I discovered when I did my lab was that I had way more potassium chloride than I should have had. But I don't think it was because I actually had more potassium chloride. I think it's because I actually had too little, not potassium nitrate, sorry, because I actually had too little sodium chloride. So my potassium nitrate was higher than it should have been. But the two things are in a balance. If one goes up, the other goes down in that math equation. They're inversely proportional. So if you got one that gets higher, the other has to get lower, because the two of them together have this relationship. where it's called inversely proportional. So what ended up happening was, and I'll show you some slides before you go and watch the video on your own, but at the end, I needed to boil all the water off of the sodium chloride to try and reduce it to the driest I could get it. And in the process, it got really viscous and thick. Instead of being like a watery solution, it became almost like pancake batter. And the hotter it got, the more it bubbled. And I had to raise the ring up on my ring stand, and I had to lower my flame because it bubbled so much that it popped, and globs of sodium chloride came flying out of the beaker all over my counter. So my countertop was covered with little spots of salt, even got on the floor. I had to go get the floor clean. So
I have a question.
yeah.
Did anybody get hurt?
No, because it was just me, and I had my eye protection on, thank goodness, because that could have been bad. But yeah, I had hot salt flying everywhere. But yeah, it got all over the counter. So that means that that portion of the sodium chloride that was on the counter didn't get included in the mass, which means it's lower than it should have been, right? So because it was lower, those calculations were lower than they should have been, that made the potassium nitrate higher than it should have been. So I think that's why my results were not quite what I was looking for. I'm going to show you those in a minute, but let's keep going over here. So let's see. All matters made up of, you guys all know this one. What is it? All matters made up of what? Well, anything. Atoms. Molecules, atoms. Yeah. Okay. So atoms is what we're looking for. Have you seen there's a joke, sometimes it's on t-shirts or memes. It says, never trust an atom, they make up everything. Have you seen that? Never trust an atom, they make up everything. Think about it. It's a dad joke, but it's true, right? They do make up everything.
I've heard that joke before.
Have you? Never trust an atom. They make up everything. Okay, so, and what were our two types of mixtures again?
Homogeneous. Heterogeneous.
There you go, homogeneous and heterogeneous. There you go. All right, who wants to give me an example of a homogeneous mixture? Who wants to try? Come on, Abby, you look brave. I mean, sorry, no, is that Ella? Ella looks brave. Ella, you look brave. Come on, Ella. No? Okay. Oh, look, Eleanor's cat. Eleanor's cat wants to give us an answer. No.
Coffee?
Ozzy, what is it? Ozzy, speak.
No, leave him alone. How about you? Do you have an example
Chocolate.
of a homogeneous mixture? Okay, chocolate milk, he says. That's probably not too bad, right? Now, there are going to be some parts that settle down at the bottom. You know, you get the thick stuff at the bottom sometimes. But
Like the chocolate gets stuck on the bottom if you make your own chocolate milk.
yep. Mm-hmm.
Chocolate
It's
is
pretty
so
homogeneous,
soft.
yeah. There's another type of homogeneous mixture. There's solutions, right? We talked about how we're using solutions. Earlier.
Coffee.
What now?
Coffee.
Coffee. Good, Jules. That's good. Yes, coffee. There's another type of homogeneous mixture that we didn't discuss yet. It's called an emulsion, and I'll give you a great example of an emulsion. The best one to remember is mayonnaise. And the way an emulsion works is basically it's like you take the particles are so well mixed that the actual molecules are kind of all surrounding each other. So mayonnaise is actually, it's like eggs and vinegar and oil that has just been whipped. And my great aunt used to make hers by hand with like a whisk. Like she would make, do you know how long that takes? It takes forever. But
Mayonnaise.
what happened? What now?
Mayonnaise is disgusting.
Oh, you don't like mayonnaise? Oh, I do. But if you ever left it in the sun, what happens
My
to
friends made me food one time, and they put a bowl of mayonnaise, and I was blindfolded, and I ate it. I
Oh.
ran to the trash can.
Do you know what happens if it gets warm?
Oh.
It's a physical
Even more
change.
disgusting.
It
Even more
separates.
disgusting.
The oil comes out, and you can watch it separate. And
Yeah.
actually, when I was a little girl, my family took a trip to the mountains, and we didn't take a lot of vacations because my dad owned his own business. But And he was always very busy. But we took a trip to the mountains one weekend, and my dad ordered a steak and a baked potato, and he wanted sour cream for his baked potato, but he also had a sliced tomato on his plate. So he wanted some mayonnaise to dip the tomato in. And they brought him 2 little cups and put him down, and it was a dimly lit place. Well, my dad kind of absentmindedly dumped the mayonnaise in his baked potato, in his nice hot baked potato. And he realized what he'd done, but he was embarrassed because it was gross. Like it was melting all out. And he realized what he'd done, but he didn't want my mom to see it, I guess. So he kind of like, he put his hands over it real casually like this, like it was all cool. And I don't know what it was, but my mom noticed, and she got so tickled that she laughed hysterically. Like the whole restaurant was staring at our table. She was falling out of her chair laughing at him. Like, what is wrong with you? But I mean, they've been divorced years and she still teases him about it. So, all right, we're gonna do something with our thermometer that we've had in this jar before we move on. So I don't know if you guys can see because it's blurry, but Drew, what do you think here? It's more like 60, I'm gonna say 68, 69, okay? It was 72 before we put it in here. So where'd that rubber band go that you were just messing with? Because it was part of my supplies and you did something with it. Oh, here it is, okay. So I have steel wool, okay? And I have a little cup of vinegar. And I'm gonna dip the steel wool in the vinegar. And I'm going to, I'm trying not to let it drip everywhere. Okay, it's gonna drip everywhere anyway, gross. I'm gonna wrap that around the bottom. Oh, that's good, juicy. I'm gonna wrap that around the bottom of my thermometer. And while we look at the next thing, I'm gonna stick a rubber band on it here to keep it on. I want it to stay on nice and tight. Get on there. It's so slippery. Okay, and it doesn't want to stay because it's so wet. Gross. It's thingy. I am flinging vinegar all over the place. Yeah, the joy of science. Okay, there we go. I had to go around it like 80 times. All right, I'm gonna dip it one more time. And I'm gonna stick it in here for a few more minutes and we're gonna come back and look at it, okay? All right, okay. So I wanna look real quick at some of this, sorry, trying to get the vinegar off the computer. I wanna look for a minute real quick at this lab because I wanna make sure you guys have a clue what you're dealing with before you start doing it yourself because it's a little complicated. You guys are just going to be like responsible for kind of watch.
I have a question.
Yeah. Go ahead.
How are we going to do the lab without the supplies?
You're going to watch it this week. Yeah, you missed the email, so you probably didn't catch it, but
sorry.
That's okay, baby. So all you guys are going to do is you're going to watch this lab is a video, okay? But what I want to show you guys is how the math works a little more slowly than it is in the video. Because in the video, it just kind of clips by. Oh, wait, that's the wrong one. This is my make my classroom thing. I wanted, where'd it go? Oh, shoot. Okay, hang on, I'll go this way. This thing took forever to make, but it turned out good, I think.
You think?
I hope. All right, goodness sakes, you know. When I have Zoom open, like everything else wants to take over and make it impossible to see. There we go. Yeah. That's why I didn't move it to the file where it belonged, and that's why I couldn't find it. All right.
I can still see classifying matter.
Can you? All right, let's make sure you can see this here. You see that now?
Yes.
Lab screen, everybody see it?
Yep.
Okay, so yeah, I know, that's my Bitmoji, I'm cute.
I can see it.
Yeah, so there we go. All right, so I just want to show you guys, the video is going to go through all of this for you, all this stuff over here. But I want to make sure that you understand this math part, or at least have an idea of what just happened, because I don't want you to watch the lab and be like, what just happened there? I have no idea. So when you get towards the end of the lab, and we've managed to get the mass of our salts, what we do basically is we weigh the beaker with the salt in it, and subtract the beaker, and then that gives us the mass of the salt. That makes sense, right? Like if you had if you wanted to know, oh, you ever been strawberry picking? and they give you a basket to go pick with, they already know what that basket weighs.
Yeah.
So yeah, they already know what the basket weighs. So when they weigh the basket, they subtract that, so they know just what the strawberries weigh. Same thing here, right? All right, so we have our numbers then. We know that we end up with 10.3 grams of sodium chloride and 7.4 grams of potassium nitrate.
Wait, what?
Yeah, that's what I knew people were gonna say.
There.
So when you do the whole lab, you're gonna end up with 2 beakers, okay? When you watch the lab, we ended up with 2 beakers, all right? One of them has sodium chloride in it, and the other has potassium nitrate in it. Like this, for example, this is the one with the potassium nitrate in it. See how it's inside? And the one with the sodium chloride
It
was,
looks like ice or crystals.
yeah, it is crystals, it crystallizes. See, there's the sodium chloride. It's pretty, yeah, it's really pretty. So there's the potassium nitrate again. Here's the sodium chloride again. Uh-huh.
Okay. For a second, I couldn't hear you,
Oh.
and I was wondering if you could hear me because it fixed it.
I hear you now. You good?
Okay.
Okay. So we're going to take these 2 beakers, all right? And then what we did is we end up taking, we're going to put it on the balance, and we get a mass for the beaker plus the salt that's in it, right? But before we did any of that, we got the mass of just the beaker. So when we subtract that, we know how much the salt is. Does that make sense? Does that part make sense? Kind of like I said, when you go strawberry picking, if you know what the basket weighs, and then you weigh it with the strawberries and subtract the basket, you know how much the strawberries.
Pretty sure it makes sense.
Yeah, okay. So then what we did after that, and this is the part I wanted to show you, these 2 steps here. And I don't want you guys at junior level to get freaked out about it. Really, this is more for the upper level guys to make sure they fully understand, okay? So we're gonna take our information here. Here's where we got, hang on. Okay, so we get to this page. All right, this looks like craziness, but I'm gonna show you, it's really not too crazy. So it asks you how many grams of potassium nitrate and sodium chloride would be found in a liter of your solution. Okay, so the solution that we work with in the lab is only 10 milliliters. It's not a whole liter. So if you know how much sodium chloride is in 10 milliliters, then you can figure out how much is in, what was it, 50? No, it's 50 milliliters. Sorry, I had to think. But then you know how much is going to be in your liter. So here's how it works. 50 milliliters, sorry, is what you used, right? So you ended up in this lab when we do it, we ended up with 10.3 grams of sodium chloride in a 50 milliliter sample. Okay, so we had 50 milliliters of solution, and there were 10.3 grams of sodium chloride in that solution, okay? And 7.4 grams of potassium nitrate in that solution. So there's 2 ways for us to find out how much it would be if we had a liter, okay? So one way, and this is probably more familiar to you guys with the way you do math right now. So if you think to yourself, well, a liter's how many milliliters? It's 1,000, right? A liter is 1,000 milliliters.
Yes.
So somebody tell me, how many times does 50 milliliters go into 1,000 milliliters?
Uh,
Can you think?
20.
20. Oh, look at this. Goes in 20 times. So if you're going to multiply the water in your solution or your solution by 20, then it's going to be what we call a conversion factor. So you're going to take your 50 milliliters of solution and multiply it by something to get 1,000. And you guys said that's 20, right? So if this is a fraction, which is this right here, it's this right here, you're 10.3 grams per 50, right? So that's a fraction. Per means fraction, right? So if you've got this here and you're gonna take 20, then you're just gonna take 20 on the top too, because basically it's keeping the fraction ratio the same. So if you do the multiplication, you end up with 206 grams per liter, because you started with 10.3 for every 50 milliliters. And then if you do the same thing with potassium nitrate, you're gonna get here. Does that make a little sense? I mean, it doesn't have to make perfect sense right now. We're gonna do it more. Little?
Maybe a little bit.
A little bit, okay. The other way to do this which is an important way to learn it for chemistry, but I'm gonna, like I said, we'll be doing it a lot more, but I'm gonna hold the older guys more responsible. It would be great for y'all to learn it too. But if you're not quite there yet, that's okay. And that is this method, which is kind of the more traditional method for engineering and chemistry. So this is using conversion factors too, but it's a little different. So here's what we had. We know we had 10.3 grams of sodium chloride for every 50 milliliters of solution, right? We figured that out. So here's where it gets interesting. The way this works is you want to find what you have that you want to get rid of as far as units go. Units being grams, milliliters, liters, okay? And you want to find what you have as far as units that you need that you don't have. So we're trying to go from grams per milliliter to grams per liter. So what needs to stay on the top?
Grams.
Grams, right. And what needs to change on the bottom?
Milliliters.
Yeah, right. We don't want milliliters, we want liters. So what we want then is a conversion factor, this right here, that will allow us to get rid of milliliters. And here's how you get rid of it. We're gonna take this, because this is 1,000 milliliters and is one liter. So this equals 1, okay? Hang on one sec, Eleanor, I'll get you, 1 second. And then that allows us to do this and go, oh, no more milliliters. We don't need milliliters on top and bottom. If they're both on top and bottom, we can just get rid of them. Just totally get rid of them. So that leaves us with grams per liter, right? And then all you do is just multiply across. And that's what you get. And we want 1 liter, right? Not 50. So when you do the division, that's what you get. So I don't want you guys to panic about it, but you're gonna see it in the lab and you might be like, what the hey? All right, Eleanor, did you have a question?
It isn't really a question, and this is sort of off topic, but
Okay, you can go ahead while I switch the screen back.
did anyone else hear that they're making a Shark Boy and Lava Girl 2
I did
in
not.
2021? They have a kid together.
I did not.
I'm sorry that that's off topic.
No, that's cool. That's cool. I don't think that's one I ever really, I don't know. Did we watch it when you were little? I don't.
And I also made Planet Drool on Rico one time.
Oh, okay. Awesome. All right. So before I let you go, we're going to look and see what's here. Okay. All right. So we were at, what did I say? Does anybody remember what I said?
60.
68, 69? Okay, so it moved a teeny bit. It's not 68, 69 anymore. It's more like 67, 66, 67. Does anybody know what happened? Anybody want to guess?
Maybe
Temperature
the
drop.
got warm.
Yeah. Why do you think, Sonia? Sorry?
Maybe it got warmer.
It got cooler by like a degree.
Oh.
I think so. Maybe it's messed up, but oh no, it's really dropping. I don't know if you can see it, but it's really dropping. Nobody wants to guess?
The vinegar dropped.
Look at
The
it.
vinegar was colder than water.
Vinegar was colder. Okay, maybe.
Also, she has it in the air now, which is probably, you know, helping it.
So here's the interesting thing. It even did what it's supposed to do. It should have gone up, and that's curious to me, because what you should see is a rise in temperature, and the reason you should see a rise, so this was a big old fail. Sometimes science fails, doesn't do right by you. But when you get when you put the vinegar on the steel wool, it's an acid, so it kind of removes any of the coating or covering, and then it allows oxidation to start, which is rusting. And when the rusting starts, that chemical reaction releases heat. So it should be warmer, but it definitely did not go warmer. So we tried and it didn't work, but hey, sometimes it doesn't work. So if you have not already submitted your
Rico?
or your Rico. Yeah. If you haven't submitted your work online or your Rico, you guys can go ahead and get that to me. I'm gonna extend. Oh, hello, Kitty. Is that Ron?
Yeah.
Yeah. Okay, cool. We're gonna extend the. I'll extend it till tonight. Upload, because I think some of you might have gotten booted out. So we'll make sure that that gets done. And then Eleanor, you got a question?
How do we submit our work?
So if you go to your grade book online through Teacheries, there will be in the assignment, if you look at lesson 3 weekly notes and homework assignment, there should be a button there that you can click and it will let you upload your work.
I'm gonna watch video and do my lab 3 and then turn in my own.
Yeah. Yeah. So it should let you upload them all as a there you go, as a PDF. All right. And then I'll get to everybody about Rico's when I've seen them all because they're all trickling in. Does anybody have any questions? No? If you've got older siblings with you, you should probably watch the lab with them. If not, watch it on your own and, you know, do your best with it. This is like a trickier one. Next week's is not as tricky. Next week's will be very visual and very obvious to see. Yes, Eleanor?
Do the older siblings have to be in the class to watch them with?
Oh, no, of course not. But if you have somebody with you that is watching along with you, it might help if you get stuck. But I'm telling y'all, don't worry.
They're coming on Thursday.
Oh, I heard he had a birthday, right? Didn't
Who?
Cameron have a birthday?
I think his birthday's coming up.
Yeah, I know it's coming
I'll tell him
sometime.
happy birthday for you.
Cool. All right. Anybody have a question?
When do we
Jocelyn?
show Rico? The drawing of Rico.
Yeah, send him in. Just text him or email him to me, and I'll have a look at him, and I'll look at them all and make some calls. Okay. And we'll see how things go for next week. Hopefully everybody's better around here and nobody's like coughing and being questionable. All right. All right. I guess I'll see you guys later.
I'm just sneezing because of allergies.
What'd you say, Senya?
I'm just sneezing because of allergies.
Oh, I know. It's awful. All right, guys. See you guys later. Bye, y'all.
Bye, Lily.
Bye.